All right. Well, welcome back, Steve, and welcome my other half, Dylan. So we're going to be talking to Steve today about Teranode, but before we start talking about Teranode, let's just first cover. So Steve, announcement came through that your colleague, Mate, who I've had the pleasure of meeting, is taking over as CTO of nChain. Before I let you talk about the transition, I want to give my own appreciation. I vividly remember we were both in Seoul, and obviously that was the next CoinGeek conference after CoinGeek London, where BSV first happened, or I guess was announced. And I remember your presentation at Seoul as CTO of nChain made me completely, it was one of those things where like a weight was off all of our shoulders, because I was very happy that the node was in such good hands, because you said specifically that you wanted to make yourself irrelevant, and you wanted to remove all the power from you guys as the node maintainers. So I just want to extend my own appreciation for how great of a job you've done as the maintainer of the client, and especially as the CTO of nChain. So I just want to say thank you for that. But then I just wanted you to talk about maybe that. So Matei is stepping into the role of CTO, and you just want to comment on that.
Yeah. So I gave a presentation at CoinGeek London, I think just after the Genesis upgrade, and I think I stood on that stage and said that Mateo was one of the best damn coders that I've ever seen, but he's also competently run Craya for many years, and in fact, in the time since Craya became, part of nChain, he acted pretty much as my right hand. So I have a huge amount of confidence in Mate, and I think that steering the nChain ship is in good hands. I think. Yeah, some partial explanation is probably due. I moved over to London, 4 years ago, I think, and came over to lead a small dev team to build something called Teranode. And it wasn't long before, events kind of cascaded, and all of a sudden we needed to build, we needed a node implementation, quick, smart, and almost ended up with a hash war, etc., and a few other kind of things behind the scenes. So I actually kind of found myself in quite a different job to the one that I had moved over to London to do. And I was, of course, happy to do that. It was an absolute privilege to be able to sort of lead the nChain engineering team through that whole experience. And then find ourselves in a position of having a whole blockchain to kind of take care of and work out how to ensure all of the infrastructure was there. So that kind of sidetracked me for a significant amount of time, and loved all that work. We had to deal with some sort of explosive growth inside the company. But at the end of the day, I had come to build Teranode. And what's probably not a well-known thing is that because of all of that other stuff that happened and other priorities with BSV node and things like that, we really didn't get to start serious work on Teranode probably until much later than many people think. But nChain continued to grow, and its commercial side sort of started to become more and more imperative. And I suppose what I can say is the day-to-day life of a CTO of a 50-person company is very, very different to the day-to-day life of a CTO of a 280, I think, they're up to now. It's a lot more sort of organizational management heavy, etc., which is frankly not my strength, and probably not my passion. My passion was always for Bitcoin infrastructure. So whilst there is a pretty significant element of sadness, because that team that grew in nChain whilst I was sort of sitting in that role, a set of people who I have extraordinary respect for, and some of them really are like family. So there's an element of sadness to be moving out of that role. But it is actually to do what I really actually came here to do, which is get Teranode over the line. So from my point of view, my day-to-day has changed. and I'm able to actually focus 100% on Teranode and other infrastructure issues, etc., without a lot of the day-to-day kind of management stuff. So I'm actually quite excited about it because I get to bounce out of bed in the morning dreaming about whatever problem it was I went to. Thinking about whatever problem it was I went to bed thinking about last night, and hopefully solving it. So,
Well, it would be interesting how everyone's paths would have changed had the hash format happened. So, but we can move on from there. So let's just jump into Teranode, right? So, I guess from a high level, and correct me on anything that I say incorrect, but so the node software itself right now is pretty much designed as an all-in-one toolkit. It's made with the assumption that the node itself is going to do everything from hashing, transaction validation. It's all done vertically instead of horizontally. So could you just talk about, just from a high level before we kind of get into the weeds of, what is the architecture philosophy of Teranode that's different from the current node software?
If you draw logical diagrams, I suppose, of a lot of the internal processes that go on in Bitcoin D, and compare them to how we're doing it with Teranode, a lot of it is actually quite similar. But you're right that Bitcoin D is fundamentally built as a monolith. I think it would be feasible to break up some of the functions in Bitcoin D and buy a little bit more time, but the way a lot of things are done are fundamentally dependent on having everything in a single place. And the biggest problem that you have with that I think people think about with distributed systems is what I call data locality. If to do a calculation or provide a function, the data isn't nearby, then all of a sudden you've got this big latency issue to deal with. That is actually still a problem with distributed systems, with monolith systems. It just happens in a slightly different way. Whereas we think it's terrible if we have to do a network hop to retrieve a piece of data to do the next calculation. When you're talking about single systems, there's a huge difference between the data actually being in a CPU cache versus being in some other part of memory, or even worse on the local disk. So they're kind of similar problems, just at different scales. Yeah. So the UTXO database is actually probably the thing that has changed most fundamentally. But the general idea is that you can split work up amongst independent nodes, I guess when we get into a little more detail, I'll show you a bit of how that actually happens, because it's not actually terribly innovative. It's a thing that a lot of distributed systems that are outside the Bitcoin space do, and it doesn't do it in a particularly different way. But that does change some dynamics, and it changes the way that you measure performance of the system, and it changes where bottlenecks tend to arise.
So could we maybe start with like a breakdown of all the different things that the node does right now? I mean, so you have hashing itself, which is essentially completely unrelated to, hashing itself is just its own function, right? It has really nothing to do with, it shouldn't really have anything else to do with transactions. It's just kind of trying to solve that puzzle, right? So you have hashing, like you said, there's a UTXO set. So all the miners have to hold the UTXO set. What are all the pieces that are right now just all packaged into one?
So I guess I'll talk about the functions as opposed to the components, because they don't map exactly one for one. The first step, I suppose, is you can see this by looking at section 5 of the white paper. Collect transactions from the network. And these are basically new transactions. They need to be validated. So there's a few steps there. There's some checks that you can do, a set of rules. Every single one of the rules needs to pass. Some you can do before you, when you've just got the raw transaction on its own. And some require you to go and fetch the inputs of the transaction, which are the UTXOs that you're now attempting to spend. So broadly speaking, you can break it up into a prefetch stage, a fetch stage, and then a post-fetch stage. And after that, you have enough information to be able to determine if a transaction is valid, if it's been double spent, which is part of it being valid, but there are some rules that well, I'll get to that in a moment. They can be reused in different contexts. And then it's basically eligible for entry into what we traditionally call the mempool. And that is a set of transactions that have been validated and haven't yet been put into a block template. The next major function of a node is to actually build block templates. That is what provides the header that is hashed over and over again by the ASIC units, who are probably not in the same data center. They're probably owned by different people. And in fact, that is the first sort of step that Bitcoin did take in 2011, I think, or maybe it was very late 2010, towards distributing the work of the node, which was when the hashing part actually got separated out and could be performed by GPUs at the time and ASICs now. Yeah. Then, of course, there's block validation. And typically when we think of block validation, we're thinking of external blocks, as in blocks that have been sent to us by other peers. And it's quite similar to transaction validation, but there are certain shortcuts that you can take. So to optimize that, you can actually follow a different sort of pathway through the Teranode, through different kind of functional handlers that apply different logic to it. And the other kind of key thing, of course, is the peer-to-peer component. How does the Teranode talk to each other? And this is sort of evident in the way that we, if anyone remembers the demonstration that we did in Zurich earlier this year, I think it was, June. We focused on those sort of validation paths. We actually didn't have any peer-to-peer connectivity at that time. Oh, sorry, the functionality was built, but it wasn't connected to what I was demonstrating. We were actually just feeding streams of transactions directly into the validation code paths there. But I mean, that has actually all been integrated now. So that's a fairly kind of important functional piece. And yeah, so you've got these sort of individual pathways of work that are loosely related. They're connected to each other essentially through the UTXO database. And sometimes some components need to let other components know about specific events. For example, peer-to-peer handler probably needs to know if a transaction that it has received turned out to be invalid, because it will want to ban the peer on the other end. But they are, you know, still quite sort of functionally distinct and separate. And what we see in a node over the course of an hour or so is, during certain periods, some of these pipelines will be very, very heavily loaded. For example, when you just, you know, received a block, the block validation pipeline suddenly comes to life. And others will be, you know, just sort of sitting there idle at various times. Yeah. So yeah, that's the functional components. I guess we'll look at how some of the fundamental architecture and how this works next, perhaps.
Yeah, that's, maybe could we just start from you know, I broadcast. So I guess maybe it makes sense to start from, if I'm a miner, the UTXO set itself, right? So how does the UTXO set change? I'm guessing from what you were just talking about, transaction validation is going to be a matter of, is it branching out depending on how complex the transaction is? Does this transaction depend on other transactions? And okay, this has a heavy dependence on other transactions, we'll offload that to this process.
Yep.
How does that change?
So let me just kick off my whiteboarding app, because it probably helps if I can draw a diagram or two.
Okay.
Okay, is that visible?
Yep, you're good.
Where's my mouse gone? Let me just move these over. So you mentioned, do we break them up based on how complex they are? I don't want to overcomplicate this, but yes, that can be done. the way you would handle, let's say, a group of transactions that you already know happen to have internal relationships to each other, parent-child, for example, you can validate far more efficiently if you do things in a slightly different order. If you have a really, really massive transaction, you might have a handler that's sort of dedicated to handling, those large transactions in a more optimal way. But to keep it simple, I'm just going to focus on, normal, simple transactions, I guess. One of the, I guess, key concepts in Teranode is sharding. And when I say sharding, I'm not talking about the same thing that Vitalik talks about when he talks about sharding, splitting the work amongst multiple untrusted parties. We're talking inside the boundaries of a Teranode. Everything is trusted, essentially. There are many, many cluster nodes. We refer to them as C nodes internally because we did start calling them nodes, but that obviously confused everybody. And we need a way to kind of break up the work. So let's sort of start with the concept of sharding. Sharding is breaking up a key space. And if you think about Bitcoin, there's a very obvious key space, a key that's used to reference transactions, which is the transaction ID. Now, it's essentially a random number. It can be manipulated to be sort of slightly less than random, but it's pretty good for our purposes. And a really simple sharding scheme would be to say, I've got, possibly I should have a pencil, not an eraser. I've got two possible boxes. These are C nodes, cluster nodes. That could handle this transaction. This is the peer-to-peer network, and the transactions come in, and we take a look at its transaction ID. And let's say our simple sharding scheme, we're just going to look at the very first byte. If the very first byte is 0 to 7, sorry, the very first 4 bits rather, then we will send the transaction up here. If it's 8 to F or 15, if you're not used to hex, then we send it to here. Now, this might just be the very first stage. Let's call this prefetch. And there might be a bunch of other steps as well. And in fact, it might bounce around in different places because of different characteristics mean it has to go to different parts of the cluster. But because we do all of this sort of work splitting based on this, what we call a shard key, which in our case is actually just the transaction ID, we can predict exactly which one of all of these boxes something is going to be on. So let's say these are all the prefetch boxes. And then we have this other set. In fact, we've sharded this one into 4 because there's a lot more work here. And we'll call these the post fetch. And so in this case, this one is 0 to 3, 4 to 7, 8 to, what is it, 90A, B to F. Not sure if I've got that quite right. So now I've done some work, and now this needs to be routed onto the next cluster node to handle that. Well, this transaction just happens to have a shard key of 6. So from the moment this transaction actually comes in, I can already know with certainty that it's actually going to get handled by this version of the prefetch handler, and it's going to get handled by this version of the postfetch handler. And that's actually an incredibly useful property because it gets even more important when we're talking about stateful handlers that have state attached to them, like, for example, the UTXO-DB. Let's say that this is now UTXO, set of UTXO handlers. It means that if I'm going to search for something, I always know exactly which one of these shards it's going to be on, which maps to a particular C node. So when I bring in a transaction, let's start by drawing a transaction. It's the typical sort of diagram, and it's spending a couple of different inputs. And this is the one I'm now trying to spend. It's got 2 new outputs and let's say 3 inputs. Right, so this one, and we're spending this one. The first thing we actually do is send off a store request to the database, to the UTXO database here, to store the new outputs that have appeared. And that's because we just want to make sure that they're there as fast as possible in case a new transaction comes along. Now, once we've done that, we actually need to go fetch our inputs. And this is really convenient because these are all, the key is the same as the main transaction ID here. So that's, you know, that makes things a lot more efficient. But when we are fetching the inputs, we have to potentially cross shards because these transaction IDs on the input side are essentially random as far as we know. So from this prefetch stage, I'm actually probably sending out a request to possibly up to 3 of these different shards. A couple of them might happen to end up on 2 of the UTXO shards, but that's by the by. It's going to be a maximum of 3. But that's the important part, is that I know which one to send these requests to, so there's no kind of wasted traffic. Now let me just try moving this out of the way. Okay. And that kind of brings us to a next step, which is a fairly important concept in Teranode, which is what we call a collection. So let's say this is now our post-fetch set of handlers. And again, we're back to the original sharding scheme because they don't need as much resource, 8 to F. So let's say I have sent this request out and the inputs, the 3 inputs that we're looking for just happen to be on that one, and that one. Now they will have to come back to a common place. So once the UTXOs from the inputs are fetched, then they can all go into a single place where the actual validation can occur. So that again happens based on the original transaction ID. And they'll end up back here in this first shard, 0 to 7, because the transaction ID is 6. And this is a point where we can, you know, validate all the scripts, determine whether these are actually all spent or not. Because when we go and grab this one here in the 0 to 3 shard, we might find, yeah, it's there and it's unspent. But that we can't tell if the whole transaction is valid at this point because we can't see what's going on in the 8 to A shard or in the B to F shard. So once we collected all 3 of these, we bring them all back and we can see if it's actually spent or not. And we do some, you know, kind of preemptive stuff here, like actually marking them as spent before we know for sure that they are spent, because we can come back later and kind of sort that out. So that's the basic sort of sharding structure, and that's why Teranode can grow, because we can take any workload and split it amongst any number of machines, and we have a reliable way of knowing where a transaction is at any moment in time. It's not always important to know which one of those machines that transaction is going to be at a particular moment in time. It's only important if the function that's performed on that particular cluster node is stateful. If it's a pure function like validate a signature or something like that, then it doesn't matter where you do it. But for simplicity's sake, we just use this this sort of sharding scheme consistently all the way through.
It's actually a pretty elegant way of handling it. I mean, it's interesting that it's kind of built into the transaction ID itself, but that's cool to see.
Well, this is I guess one of the, I've made a comment a few times before. The more I've actually looked into building a scalable version of Bitcoin, the more I realized that Bitcoin was obviously designed from the ground up in this way. If we didn't have the UTXO model like this, I don't think that this structure would not be as possible, or at least it would be a hell of a lot more complex to build and implement. Yeah.
Okay. So this is all transaction based. So I guess, I mean, so now in the post, is that where we start building the block? Is that where the miner would start building the block, or is this kind of completely?
So what I've drawn here, this is really just TX validation.
Sure.
After that, I seem to be drawing in highlighter. After that, we then go off to block template builder, which is, oops.
But so this could theoretically be done by someone separate from the person doing the hashing, right? I mean, this could be locked in some kind
of. Yeah. Well, the person doing the hashing is in this model is more than likely still some third party,
right?
In the same way as with a mining pool. So we're maintaining the get mining candidate RPC interface, because about a bit of backwards compatibility is obviously going to be important. But I actually can't see any particular reason for that model to change. I think people already understand how to scale the hashing part of Bitcoin, because they're doing it right now. They've been doing it for a long time. This is about the collecting of transactions, ordering them, putting them into a block, and building a template. That's the most important part of work, piece of the work that Teranode does, as well as, of course, validating other people's blocks.
And I think listening to you talk about this in Zurich, the idea here is that when you guys release Teranode, you have some implementation of a TX validator, but the idea could be that if you're a competing service and you want to develop a proprietary component, you would just plug this in here, right? Like this is the component that you guys would develop from the first implementation, and then third parties can substitute the proprietary TX validator.
Yeah, big. If you can build something that is faster, does the job better, provides another feature. The architecture is relatively straightforward to just pop a component out and pop a component in its place. If you think about the, these, can you see my little cursor there? Yeah. Okay. You think about these components here. If you assume that this component is just a UTXO database, if you can build a UTXO database that's faster, as long as you maintain these incoming and outgoing kind of APIs, then you can drop throw in a drop-in replacement, essentially. Yeah. But these whole pipelines are actually even designed to be replaced if necessary. If this is really simplistic, because we've just got prefetch, UTXO, and postfetch validation here. There's probably more steps internally. But if you decide you don't like the way that we're doing the validation, then the incoming transaction validation, you can replace that pipeline, but the block validation stuff would still work just fine. And in fact, I said I didn't want to complicate this, but we actually do this in Teranode already. We have a different version of this pipeline here that does the jobs in a slightly different order for transactions that have known parent-child relationships. The difference is pretty trivial. We send off all of the new outputs to be stored first, and we wait until we've confirmed they're all done. And then we send off, and then we go fetch all of the inputs. That way we avoid any chance of a race condition where we try to fetch something that's about to be stored but hasn't quite yet. And that improves the efficiency of the system significantly. You know, otherwise, very, very large transactions, you might have a version of this this pipeline where you've got actually everything compressed onto one machine, so that all of the work actually happens right next to where the data is, because you want to avoid sending, you know, a gigabyte data stream across the network. Yeah. So yeah, and you know, it's important from a Bitcoin point of view, I think, because the Bitcoin infrastructure itself, the heart and soul of a system that is designed to foster competition, should itself be competitive. And you know, that's part of what I guess was quoted in an announcement just recently. I really want to help create that kind of competitive market on the infrastructure level, but I'm also pretty keen to be a competing participant in that market.
Sure. Cool. Okay, so should we move on to, I guess, how block building is different, or is there anything else you want to talk about with transactions themselves?
So this is a pipeline, right? And then I'm trying to think back to like the diagram that you showed before. So pipelines made up of components, and then this larger to the Teranode like framework. Does the framework have defined interfaces between the pipelines, or is it still kind of specific to what that pipeline is doing?
So the framework itself is quite agnostic to Bitcoin. Let me show you a diagram here. That's a very, very early flow diagram. It's probably several years old. This is actually the basic functional unit of a Teranode, and it's one of those boxes that you saw on the previous diagram. And this is a unit that just does a piece of work, and it basically takes a message that comes off the message bus, which doesn't necessarily mean message bus like Kafka or ZMQ or something like that. It's just a logical term. It handles the deserialization of it if it's come remotely and had to be serialized. In some cases, you can have many of these pipeline processes on a single machine. In fact, you can run an entire Teranode on a single machine just by configuring all the handlers to run on a single C node. And it handles the message decoding. This is the part that actually does the work. And it's expected that it will emit another message, which is basically the trigger for another piece of work to happen somewhere else in the Teranode cluster. And that message will have a message type and a shard key, usually the transaction ID. And then it goes through this, what we call shard queue director, which is really just a router. Its job is to get that message to the next handler in the pipeline. And of course, things can branch, because a fetch UTXO request, for example, might result in an error, and that might mean that you want to notify someone else. If the transaction has been double spent, for the input's been double spent or spent already, for example, the peer manager might want to know. So any pipeline step processor can actually emit multiple messages to potentially different targets elsewhere in the system. That's that fundamental kind of way that it's built. And each unit, of course, has its own kind of performance monitoring and whatnot that reports back to a central point, so that you've got a view of everything that's going on inside.
Was this framework like something you guys built entirely from the ground up, or did you take inspiration or something else? Like it seems like that's pretty specific.
Yes, we did actually build it. I built a significant amount of this myself, actually, during the first few months of COVID lockdowns. I had to take advantage of that time somehow. So that was when we really actually got to get seriously started on it. So yeah, it certainly looked at doing some at a whole lot of off-the-shelf stuff. In fact, there is one framework which I kind of wish I might have seen earlier on before we'd gotten substantially into building this, called Prefetch, which I think Derek Moore actually works on, which is quite similar to this. And there are a lot of frameworks that, stream processing frameworks, etc., that have these sort of internal sharding capabilities. But what we always found we were missing was control over that sharding scheme, how that sharding actually gets done. And that's not the only reason for building the framework from the ground up, but it's a significant reason, because that gave us huge amounts of control, especially at the database level. We have no dependency on the actual data store that we use for the UTXO database, because of the way that we've architected it, and because of that sharding scheme. Which means, in theory, we could use SQLite, we could use MySQL, we could use Cassandra Foundation DB, we could even write to CSV files if we wanted to, if we were that kind of nutty. And it wouldn't actually fundamentally kind of change the architecture either. Redis was an obvious starting point for us, but it suffered from the same problem, is that Redis is shardable, but you don't have any control over the sharding scheme itself. So Cassandra is probably the best one to talk about how this is problematic for us, because if we're talking about volumes that are potentially going to saturate 10 gigabit LAN segments, and you potentially have to break up have multiple LAN segments in a Teranode, you need some predictability about where you need to go to get the work done. And with Cassandra, you just connect to any node, but you don't have any visibility, any Cassandra node. It takes care of then routing your request in another hop to the internal shards that are relevant to your request. You don't have the visibility of it. Well, we needed to just go kind of one step deeper, where we actually could see where they were, so that we could connect directly to those nodes, and preferably keep that data store local if possible. It really is all about keeping the network usage down, because that is by far the biggest bottleneck in this sort of system.
And just out of curiosity, while we're on this, so output type A, output type B, when you're saying output type A, output type B, what is the type A, type B? Are you talking about the sharding based on the
so different message types? So for example, one might be a UTXO was found, I'm now sending it back to the validation handler, and the other might be the UTXO was found but already spent. I'm sending a message to the peer handler to let them know that this guy is sending you double spends.
Got it.
It could also be the whole thing just crashed. There's a bug in our code, and the whole thing actually just crashed, and we're sending it to a central error handler or whatever to wake someone up to fix the Teranode.
Makes sense. Okay. Okay, so should we keep moving along the process then? Or should we stop there and just talk about transactions and leave block building to another time?
I think, and I'm happy to do a few of these sessions. We can walk through all of the different bits. I'm trying to kind of convey a bit. This is the first time we've really talked seriously outside of nChain, I think, about how it's structured and architected internally. So I don't want to throw it all on the table in one session. Yeah.
So then let's stop there and maybe just ask some general questions about, from a developer's perspective, does anything change on how they, I mean, obviously, fetching UTXOs for developers is really important. It seems like nothing really changes. It's more of when you make that fetch request, how the node you're getting that fetch request from handles it. But from a developer's perspective, does anything change, or probably not?
It shouldn't do. No. I'm not a huge fan of the Bitcoin RPC interface, but I recognize that it's in such wide use that we would be a little bit crazy to release Teranode with something completely different. So I think we will probably aim to have something different at some point in the future, but it will have to have the RPC interface. So the way you do most things should be similar. There are some RPC calls that just don't make sense in a Teranode, for example. There's a get memory pool call, which is should have been long since deprecated, but there is sort of no kind of real sense of the mempool itself in Teranode. And some that are quite complicated to implement. So we've actually gone through and broken down and prioritized all of the RPC calls, because there's more than 100 of them, into what we think are actually the critical part, the absolute minimum viable to make it function, and then the ones that we think that people are using, and then the ones that are sort of nice to haves, and further down to we're not even going to bother because that's just kind of crazy. Like all the wallet functionality is not going to be there. But then, of course, we need to go out to the world and say, is this list right? Is there anything that is critical to your business that we have assumed no one is using? And are you actually using the things that we think that you are? So we'll provide as much of that functionality as possible. But if you think about Node as a black box with some APIs, it should look as very similar to old Bitcoin D.
And so then what is the future of Bitcoin D? I mean, is it, obviously Bitcoin D right now is basically just a open source client. Is that going to be maintained separately, or is it,
Look, I think it has a natural kind of end of life because of the fact that it is monolithic. It simply can't be, well, I mean, it could be broken up, but we elected to do the complete rebuild rather than try to go down that road. So someone else might want to do that, but I think it would be a very high cost exercise. So yeah, it probably will, reach a point where it just isn't usable. And this is, I guess, the tricky bit, because a lot of people are using Bitcoin D for purposes other than mining. It's being used as an index. It's essentially being used as a database because, well, it is. It's got several databases in it internally, and it's just been kind of convenient to use it in that way. In a lot of cases, I think people, if their business model is dependent on it, then they probably need to have a look at their business model and see if their business model can bear the cost of running a Teranode to still be able to provide that service. Otherwise, they need to kind of look at alternative ways of doing things, and that's why we have the Light Client program under the BA infrastructure to try to help people find those alternative models. Yeah.
But so maybe like, and Dylan, I feel like you're probably about to ask a similar question. So what developers are doing right now, quite wrongly, in my opinion, is if you're creating some kind of application and you need to stay in sync with the UTXO set, it's really poorly managed between, either they are running their own node, which probably makes zero sense, but because you're still on the outside of the network anyway, it's not like you're that in sync all the time. But I guess my point is, it seems like, and this is what probably has been hinted at for a while, is there will just be distributed sets of nodes that run just the UTXO set and are doing the transaction validation that you would be highly connected to stay in sync. Instead of, right now, it seems like in order to stay quote unquote in sync, you need to run the entire Bitcoin D node or connect to someone that's running the entire Bitcoin D node, whether that is a miner or not, which seems pretty inefficient.
I think it would be fairly trivial, and in fact, it may be a thing that we do to build a Teranode that does block validation only and maintains a UTXO set. Yeah. And that might be a service that people will either want to have run themselves, or it's a service, a third-party service that they would consume. So Teranode is designed to have these different configurations. So you could hang all sorts of indexes and things like that off the basic pipeline, and then that's why we built the framework so that it's got that kind of flexibility. But building a chopped down Teranode that just maintains the UTXO set, or even a shard of the UTXO set would be entirely possible.
Yeah, that's definitely where I was going with it. And like the indexer example is a pretty good one. Also UTXO management, which kind of ties together. I think the biggest question we get when we start talking about this to folks is like, is Teranode, from an application developer, and you need infrastructure, is the idea that you're going to take a stripped down version of Teranode with just the components you need? Is that something that the requirements to run Teranode are higher, so you're going to have to depend on another service, or that's something that someone would offer for high connectivity? Like, do you view the requirements of running a minimal version of Teranode as being high, or is it structured? I mean, clearly the framework's structured in a way that shouldn't necessarily be the case long term.
Well, I mean, it depends on what network you're running it on, because it's entirely a function of the amount of traffic there that the Teranode needs to be able to handle. Teranode is designed to be able to handle massive traffic, but it should by default mean that it can handle very small amounts of traffic. So if you run it on a reg test, you certainly can run an entire Teranode cluster in a single machine, and that, like we do that in dev. In fact, for the first year, we didn't have the networking stack and everything put together, so it wasn't possible to run it on two machines. And so we had to run two versions of it inside a single JVM, which was a nightmare. But yeah, we all do. Most of the development is done that way. We have a test cluster so that we can deploy it onto multiple machines to test various things. But yeah, I think theoretically, if the volume is low, and I think it's Teranode running on a single machine is probably about half as performant as a Bitcoin D that would be running on the same machine. It's probably a bit more than that. There's certain overheads in the framework that are just necessary in order for it to be capable of that sort of distributed operation. But yeah, today's testnets or reg tests would be simple. And if someone creates a build that is compatible with a Raspberry Pi, then yeah, they could probably run it on a Raspberry Pi. Yeah.
So I've maybe 3 questions left, and then we can try and keep this somewhat bite-sized. But the first, I guess, since this is a question that Roger had asked, the script execution itself. So he asked a question saying, is it compatible with the node, and how do they get there? I might be misunderstanding that question, but maybe more generally, he's asking if the script engine can be compiled and run in isolation for validating scripts. It seems like that would be built into the pipeline you just mentioned, but is that something that can be modularized out?
So most of the validation, most of the Teranode framework and the pipelines and handlers that we're building are in Java, but we are actually using the script engine from Bitcoin D. So it has been wrapped and a build version created, which means we can use exactly the same code as Bitcoin D. That solves a huge number of potential compatibility risk vectors, landmines that we could trip over, and we've simply wrapped that in JNI, Java Native Interface, so that we can call the C++ code, the native code from Java. There's a tiny overhead there, but because of the cost of running a script, validation usually includes a digital signature. It's trivial. So that saves us a lot of problems. We are actually working on modifying the script engine itself in the sense that we want it to be able to handle streams rather than passing entire scripts at once. And that's because we want to be able to handle scripts of literally any size, potentially not even, capable of fitting in memory. But that is being done in the Bitcoin D code itself. It's a bit of a scary change, so there'll be a hell of a lot of testing done there. But yeah, essentially they're both going to be running the same script engine, so that will be I think that probably eliminates about 80% of the risk when it comes to accidental incompatibilities. So I did a lot of work on the Bitcoin J script engine, and I know how many incompatibilities I found just in the course of doing some of that work, many of which have been there for a decade. And I'm sure that I haven't found them all yet. So
yeah, so I was kind of curious about what is the history of that engine? Is it I mean, it must be pretty good if you're comfortable just plugging it into Teranode, but does it have a complicated history, or is it?
Which one? The Bitcoin D one?
Yeah.
Well, yeah, I mean, it does have a complicated history because new opcodes have been added to it,
Right.
removed, and you know, all of the stuff that we had to do in Genesis to put it back the way it was. We try to touch it as little as possible because it is literally the place where most of the dragons live in Bitcoin code. So we need a pretty compelling reason to ever let anybody near it. But yeah, it has a huge checkered history. I will be really glad when this piece is done, the streamifying piece, because I'm pretty sure after that, no one will ever need to touch it again. And that really, you know, cuts out massive amounts of risk for the future.
So then just maybe two general questions. So the first would be, what kind of different, I mean, what new business opportunities do you see emerging from the way that the node is going to evolve into the Teranode structure?
Well, look, I mean, it's because it's extensible like that. You could build all sorts of services on top of it, and they may not necessarily even need to be, you know, you may not need to be the person providing the core who operates the core Teranode to add, you know, extra bits on top of it. You could have one person who's a miner running a Teranode, and they might offer you a feed of data for something or other from their Teranode because they've got it anyway, and then you can co-locate something next to them and use that to build, you know, token indexes or what else, whatever else, you know, Merkle proof, serving Merkle proofs is something that is not strictly speaking a function of the core node. It probably makes economic sense for it to be that, but there might be a specialist that you know, runs one of these block validation only nodes and uses it to build Merkle trees, Merkle paths, and service those as a business model. I think there's a whole world of possibilities there. But yeah, fundamentally, the framework itself is it's a way to plug into what happens in Bitcoin, but it's also a way to be able to do any kind of work that can be distributed and sharded like that. So I'd be really happy actually one day to find if people you know, find people using the open framework for stuff that's got nothing to do with Bitcoin. That would be a win. That would mean that we've actually done something that's useful in a broader context.
Sure. And then maybe a bit of a loaded question that you may not have the answer to yet, but obviously this came up and will probably come up regarding, are all the components here proprietary? Is it open source? Going to be open source? I mean, obviously Bitcoin D's history is open source, but what is do you guys have a plan for that yet, or is it?
I mentioned this in Zurich, but I will keep on saying it because I've heard different versions of this over time. There will be a complete set of pipelines, components, functions, etc., to replicate all of the functions of a node released under Teranode Open Framework. That will be under the OpenBSV license. Yes. BA themselves are not planning on building anything proprietary, but once the framework is out there, of course, it's open slather. Anyone can build a proprietary component or an extension or replace an existing bit of Teranode if they want to. Yeah. But yeah, no, I think it was important. There has to be a functional replacement for Bitcoin D that is available to everybody, to all the, you know, kind of existing miners, if we're going to be able to actually push scale past the point where Bitcoin D dies. Yeah.
Yeah, that's good to hear. Okay, I don't think I'll ask any of these other questions just yet, and we can save them for next time. Is there anything that I didn't ask about? And I guess I'll give the disclaimer to the audience that I definitely am very ignorant on infrastructure and things like this. That's why Dylan's here. And also, so if I ask any ignorant questions, I apologize in advance. But all right, yeah. Is there anything else you wanted to cover before we stop for today, and we'll pick it back up next time?
No, I don't think so. Like I plan on sort of talking a lot more about Teranode and helping to kind of explain some of the internals, you know, over the coming months, and probably, you know, fairly regularly. So if people do have questions, yeah, please kind of do ask. I found that it's actually been explaining internally to our own engineers and whatever how Teranode's sort of meant to work and how it's structured has actually been a really useful exercise, I think, in broadening their understanding of areas outside the code that they normally kind of work on as well. So it is even though Teranode is probably going to be mainly run by miners, it's still a worthwhile subject to dig into and understand. And of course, I'm happy to talk about it as much as anyone wants to listen, because it's my baby and my pet project. So
yeah, I mean, I think from our perspective, as we've been building things, what's become like really obvious to us that we've had conversation about this privately, but everything being so monolithic is a really, when you hear like Craig talk about the mandala network and all that kind of stuff, we don't really have a mandala network right now. We still kind of just have the small network in the middle, and everyone kind of fetches stuff from them. So I think what excites me the most about, you know, breaking these out into services is that we can at least start, you know, we can start running things that are specialized that, like you said, maybe if we just want a token index or things like that. I think that probably was what excites me the most. And that's why I asked you about the business opportunities, because I just hope other people start thinking that way of, you know, what can I specialize in that, you know, I can break out and start offering a service to someone, because I think we need more services than people are realizing right now. That's what we found. So
it also gives you more control over whatever service you're providing. It's like you don't have to maintain this giant monolithic service that, you know, has components you don't use or is not even remotely relevant to what you're trying to offer, right? So
that's it, actually. I mean, Mappy was a really good example of this. You know, Mappy introduced the capability very early on in its lifetime for miners to override fee policies and apply fee policies in different ways. And that was, you know, not just saying, oh, I'm going to apply 0.5 for this user and 0.3 for this user, but yeah, they could do something completely off the wall, like I'm going to charge 10 sats for the first 3 bytes of the transaction if they're of a particular value, and then I'm going to charge another fee rate for the rest. And the reason why miners never did that before was because to do it, you had to go into this gigantic, monolithic, terrifying code base that is, quite frankly, really is quite scary to work on. And all you had to ask the DSV team, and of course we were stuck in a pretty long release cycle, because we have, you know, minimum QA requirements and things like that we've got to go through. And so a change like that could take a, you know, really long time. But if you're talking about a really simple piece of code that says, you know, for user X, I'm going to allow this different fee policy, you should be able to do that pretty much, you know, in a few hours, maybe some testing, and deploy it in production. You shouldn't have to wait 3 months for an SV release. Yeah, so that was one of those sort of early examples, I guess, of that breaking things out makes code more agile, that I think you were referring to, Dylan.
Yes, exciting.
Yeah, great. Let's wrap for now, and we'll just keep going through all the components whenever you have time, Steve. So look forward to the next whiteboarding session.
Okay.
All right. Thank you, guys.
All right. Thank you.